Okay, today's plan is to work through sections 7.1 through 7.4, introducing the real number system and talking about some properties of the real number system. So um, there's a lot of sections on the schedule today, but I think each section, um, deals with only a couple of topics, and a lot of these topics are things we've seen before. So it's kind of a rehashing of these ideas in a new context. And I think just kind of a review of a lot of this material. So should go pretty quickly for these sections. The two quotes of the day today are in honor of Veterans Day yesterday. The first one, it's a bit hard to track this down, but as far as I can tell, it's a quote from somebody named Richard Grenier, and probably like a rephrasing of um, some ideas from Orwell and maybe Kipling. But I like this phrasing of it better than any of those. Um, the statement that we live in relative peace and comfort only because of rough men who stand ready, willing to do violence on our behalf. So, we see around the world there are a lot of folks uh, who don't have the opportunity to, sit in a comfortable, quiet, safe house and join a Zoom session and talk about math. I mean, uh, as much as you might not want to join a Zoom session and talk about math, the ability to do that is certainly not something that everybody in the world has at the present time, or even that people in our country had, throughout history. Um, and the second quote on a related idea by John Adams. This is an excerpt from a letter of his. So I edited it down, but I think the meaning it is the same as the original. I must study politics and war, I being John Adams, so that our sons may study mathematics and philosophy, commerce and agriculture, in order to give their children a right to study painting, poetry, and music. So, kind of roughly speaking, we have to get the kind of violence handled. One uh, perhaps I don't know, uh, insight of way to say what politics is the study of the use of force. Um, we have to be able to secure the country and society, and then we want to do things like farming and engineering and building roads and infrastructure and so on uh, to have enough resources to run our society. And once we have those needs met, kind of physical safety and our day-to-day just physical needs, then we can do the things that we really want to do, things like studying painting, poetry, music, etc. Um, the only thing that I would argue is that philosophy probably belongs in all three of these categories, not just in the middle category there, but um, but I think the meaning is pretty clear that uh, we appreciate the fact that there are folks who have made very significant sacrifices so that we live in reasonable comfort and security, and we can study what we want to study, take uh, pursue the interests that we want to pursue, and not have to worry about what so many people in the world worry about day to day. So, uh, just some thoughts for Veterans Day yesterday, or as some of my friends would call it, the day after the Marine Corps birthday. So, have a lot of friends who are Marines. So, um, all right. So moving on to 7.1 to 7.4. So introducing the idea of the real numbers. I like this picture from your book. People have all kinds of similar pictures, but we talked initially about counting numbers and whole numbers in this course. We kind of expanded that view to integers. We expanded a little further to the rational numbers, the fractions, integer divided by integer. And then we want to expand that a little further to the real numbers. And the real numbers encompass the rational numbers, which have as subsets, the integers, whole numbers, and counting numbers, as well as these things called irrational numbers. Now you might say, why are we calling these real numbers? Isn't this all the numbers? Why don't we just say this is numbers? Well, these are real numbers as opposed to imaginary numbers. So what's an irrational number then? It's a number whose decimal expansion, if I wrote it out as a decimal, does not terminate or repeat. And some examples of irrational numbers, things like pi that we saw computing the circumference and area of a circle. It has a decimal expansion that does not terminate or repeat. You cannot write pi as a fraction. You can approximate it by a fraction. You can come up with a fraction that's pretty close to what pi is, but it's not exactly pi. Even a number like the square root of 2, the square root of 4 is 2, so that's a kind of a nice square root. But something like square root of 2, if I'm looking for a number that when I multiply it by itself, I get 2, well, no integer or whole number is going to satisfy that, but also no fraction is going to satisfy that. So square root of 2 is not a rational number. And there's a formal proof of this that's kind of a classic proof by contradiction. So you start by assuming that square root of 2 is a rational number. They can be written as p over q, where p and q have no common factors, and then you do some work and you argue that p and q must have a common factor, but you said that p over q or p and q had no common factors, so you reach a contradiction. Square root of 2 must be irrational. Or something like this. Just being irrational doesn't mean that the decimal expansion has no pattern. It just doesn't terminate or repeat. So 0.1, 0, 1, 0, 0, 1, 0, 0, 0, 1, etc. That would be an irrational number. We can't write it as a fraction. I mean, we see the pattern. It has a 1, then 1 0, then a 1, then 2 zeros, a 1, then 3 zeros, but it doesn't repeat. So what's the motivation for coming up with all of these different kinds of number systems? Well, the motivation really is that we want to solve more general types of equations. We've addressed this once already, but I don't think it hurts to just go back through and recap this. So if I have an equation like, say, x plus 3 equals 4, my solution, x equals 1. So I can solve problems kind of like this in the whole numbers. Or maybe even more generally, if I had, say, x minus 3 equals 4, then solution x equals 7, we can add 3 to both sides. So if I have, say, x minus a equals b, where a and b are positive numbers, x equals a plus b will also be a positive number. Then if I go to, I skipped a step. So for x minus a equals b, the solution, here a and b are positive numbers, the solution is a positive number. It's a whole number or a natural number. So it's one of these innermost number systems here, the counting numbers, the natural numbers, or the whole numbers. If I go to something like x plus 2 equals 3, my solution, x equals 1, happens to be a whole number. That works nicely. But if I had, say, x plus 3 equals 2, my solution is not a whole number. I can't add a whole number to 3 and get 2. My solution, x equals -1, is an integer. So if I want to be able to solve addition problems, x plus a equals b, x equals b minus a, if I want to be able to subtract any two positive whole numbers, then that's an integer. I need to expand my numbers that are under consideration to the negative numbers, because it could be that b is bigger than a and I get a positive number, but it also could be that a is bigger than b and I get a negative number. So that's the integers, the next ring. What about the rational numbers? Well, here I'd like to be able to solve, say, a times x equals b, where a and b are, say, positive whole numbers. X equals b divided by a then. So I need to be able to deal with ratios of whole numbers. Or if I even had ax plus c equals b, then x is going to be, we haven't talked about these two-step equations yet, but this is something you'll see in Math 90, x equals b minus c over a. This numerator could be negative, even if a, b, and c are all positive. So we want to be able to look at quotients or division of integers with integers. These are our rational numbers or our fractions. If we expand our number system to include fractions, we can solve any equation of this type where a, b, and c are positive whole numbers. And we saw that fractions and decimals kind of had a nice correspondence. So decimal numbers are basically the same as rational numbers if the decimal expansion terminates or repeats, which is all of the decimals that we've considered so far. However, if we go to decimals, we actually can introduce new numbers. So we can look at a number like square root of 2. Oh, what did I just bold there by accident? If I look at a number like square root of 2, well, I could have an equation like x squared equals 4. What number, when I multiply it by itself, gives me 4? That would be x equals 2. That would be an integer solution. But I could have a similar question like this where I say x squared equals 2. So if I allow maybe powers to enter into the equation here, x squared equals 2 says that x equals the square root of 2 would be a solution. But this is not a whole number. It's not an integer. It's also not a fraction. This is an irrational number. It's irrational because it is not a rational number. A rational number is a ratio, right? That's where the word rational comes from, ratio. It's the ratio of two numbers. So rational numbers are a ratio of two integers. An irrational number is something that is not a rational number. It cannot be written as a ratio of two integers. So square root of 2 isn't something like, 4/3 or something like that. Even if we looked at all of the rational numbers, 10-digit number over 10-digit number, still not going to be able to find one that's exactly square root of 2. So typically we'd write the answer as either square root of 2, or we might write a decimal approximation, x as approximately, say, 1.4 or something like that. So that's the goal here with the irrational numbers. Now, one thing that we might notice is if I have something like x squared minus 1 equals 0, I could add 1 to both sides and get x squared equals 1. And I see that x equals 1, for instance, is a solution. But if I had x squared plus 1 equals 0, that says x squared is negative 1. I'm looking for a number that when I multiply it by itself gives me a negative output. I mean, this seems like a pretty reasonable equation to want to solve, especially since solving an equation like this is fairly straightforward. But I'm looking for a number that when I multiply it by itself gives a negative output. If I input a positive number, I multiply it by itself, it gives a positive output. If I input 0, 0 times 0 is 0. If I input a negative number, negative times negative gives me positive. A negative input yields a positive output. I don't have any inputs that can yield a negative output. And this is the impetus for imaginary numbers. We're not going to deal with imaginary numbers in this course or even in Math 90. That's a Math 108 topic. But just to give you, a little bit of perspective on why do we call these real numbers instead of just saying the numbers, like all of the numbers? Well, because there are other number systems. And even though these are called imaginary numbers, they're working to solve um, what seems to be, at a first glance, like a pretty reasonable equation to try to solve. I mean, if x squared minus 1 equals 0 is a reasonable equation that has a nice answer. I mean, x squared plus 1 equals 0, it seems is also a pretty nice, reasonable equation that we would want to try to solve. But it turns out that we need to expand our view past the real numbers to solve x squared plus 1 equals 0. So this is not a topic that we're covering in this course, but just to show you, what the next natural progression would be past the real numbers. The imaginary numbers, when you combine the imaginary and real numbers together, you get the complex numbers. So that would maybe kind of in some sense be like the biggest number system that you could really be interested in, at least under kind of standard algebra. If you try to like go a step further and make like another kind of number that's like an imaginary number, it turns out that you don't need to do that. So there are equations that we can't solve with just real numbers, but if we add in the imaginary numbers, then we can, in at least in some sense, solve all equations. Okay. So that's the motivation for developing these different number systems. Each time that we want to solve a little bit more general of a problem, or a little different of a problem, an equation, we might need to introduce some additional numbers to be able to write out that solution. So this real number system, this kind of encapsulation of basically all of the numbers that are not imaginary numbers, that are not complex numbers, they have some properties. So these are pretty nice properties. They have the commutative and associative properties of addition and multiplication. So the commutative properties of addition and multiplication says that the order in which I add or multiply doesn't matter. A plus B equals B plus A, or A times B equals B times A, where A and B are real numbers. Note that these properties don't apply to subtraction and division. So if I try to, come up with something like a commutative property of subtraction, is it true that 3 minus 5 equals 5 minus 3? Well, no, that's not true. 3 minus 5 gives me negative 2. 5 minus 3, positive 2. Those are not the same number. Or to division, is it true that 2 divided by 4 equals 4 divided by 2? Well, no, one side is 1/2, 2 divided by 4. The other side, 4 divided by 2 is 2. 1/2 is not the same as 2. So these properties don't apply to subtraction and division. We could kind of force the issue a little bit if we wanted. If we wanted to do 3 minus 5 and write the 5 first, we could choose to write this as 3 plus negative 5. And now I have the addition of two integers, which are real numbers. Since I have addition, I can switch the addition order. So I could write this as negative 5 plus 3 instead of 3 minus 5 if I really wanted to. But I really have to kind of attach that minus idea to the 5 as a negative number and move that around with the 5. And I can maybe do something a little bit similar with division, but it's a little bit more complicated. We would use, instead of the additive inverse, the multiplicative inverse, which is an idea we'll talk about in a little bit here. We also have the associative properties of addition and multiplication, and that says if I have a list of terms that are added together, it doesn't matter which order I add them in. I could add A plus B first, and then add C to that, or I could add B and C together, and then add A onto that sum. And I get the same result. Or the same thing with multiplication. If I have three numbers A, B, and C multiplied together, I can multiply the two the first two, take that product and multiply that against the third, or I can multiply the second and the third, take that product, multiply against the first. I get the same answer. So if I change where my grouping symbols are, I get the same answer. If I change which operation I choose to do first versus second, get the same thing for addition and multiplication. And again, note that these properties don't apply to subtraction and division. Say 3 minus 5 minus 2, if I do 3 minus 5 first and then subtract 2, I get negative 2 minus 2 is negative 4. But if I try to group it the other way, if I try to group the 5 minus 2 together and do 3 minus that, 5 minus 2 is 3, 3 minus 3 is 0. Clearly not the same answer. Or for division, if I did 8 divided by 2 divided by 4, if I do the 8 over 2 first, that gives me 4. 4 divided by 4 is 1. But over here, if I do the 2 divided by 4 first, I get 1/2. 8 divided by 1/2. Well, divided by a fraction, we invert and multiply. 8 times 2 is 16. So clearly 1 and 16, not the same number. So, but I can use the associative property on addition or multiplication. Okay, let's simplify a few things using these properties. So if I look at my first example here, I have negative 45a plus 15 plus 45a. I do see that I have some like terms. I have a to the first power in these two terms. It would be nice to put those terms together. So I could, for instance, switch the order of these two terms, the 15 and the plus 45a, using the commutative property of addition. And then negative 45a plus 45a is going to give me 0. I suppose maybe in some sense we're jumping the gun a tiny bit here because we haven't talked about the 0 property, but I think we have enough experience with this that we know how this works. The same idea would work with fractions as well. 2/5 plus 5/12 plus negative 2/5. I can switch the order of these. Again, using commutative property of addition. And then I have 2 minus 2 divided by 5 plus 5/12. That's 0/5 plus 5/12. That's just 5/12. Or if I have an example like this, where I have 3 fractions multiplied together, I know that I can use the associative property and say multiply the first two together. 7 times 9 divided by 12 times 17. That makes one fraction that's multiplied by a second fraction, 24 over 7. Now I again have the product of two fractions. I have 7 times 9 times 24 divided by 12 times 17 times 7. I can cancel some common factors. The 7s go away. 24 is 2 times 12. Looks like I have 18 over 17. 17 is prime, so it's not going to divide anything. There are going to be no common factors between 17 and 18. So I end up with 18/17 from this. And I just leave that as an improper fraction. So using the associative property here, it didn't matter which order or how I chose to group my multiplication, whether I did the first multiplication first or the second multiplication first, didn't matter. And here I have some coefficients of A and some coefficients of B that are all added together. It would be nice to get my A's together and my B's together, and I can do that by switching the order of these middle two terms. So I have 5/6 A plus 1/6 A plus 3/10 B plus 9/10 B. Or this gives me 6/6 A plus 12/10 B. Well, 6/6 is just 1, so that's just 1A or just A. And 12/10 B, I guess I could factor a 2 out of 12 to get 2 times 6, and out of 10 to get 2 times 5. The 2's divide out, and I get 6/5 B. Are there any questions on this so far? I know I'm going kind of quickly through this, but if anybody has any questions, let me know. Okay, let's take a look at the distributive property. Remember our order of operations, parentheses, exponents, multiplication, division, addition, subtraction, and roots get kind of, globbed in with exponents. Our distributive property takes us down one level on the order of operations hierarchy. So if I have A times parentheses B plus C, if I have multiplication distributed into addition, that's A times B plus A times C. That's what our distributive property for addition over multiplication, or multiplication over addition, sorry, says. I can distribute multiplication over addition this way. A couple notes on this. This doesn't apply the other way around, so to speak. We can't distribute like addition over multiplication or something like that. A plus B times C doesn't make A plus B times A plus C. Note 2 is kind of interestingly, this actually does apply to subtraction. So A times B minus C is AB minus AC. Basically, if we just replace C with negative C up here, and then A times negative C is just negative AC, or that's AB minus AC. So this actually does apply to subtraction. Multiplication distributes over subtraction in basically the same way. It does not apply to division. If I swapped multiplication, the A times parentheses, in if I swap division in for that multiplication and got A divided by parentheses B plus C, that is not A over B plus A over C. What this would be is something like A divided by B plus C. And that really just does not split up or simplify really in any nice way. So I can swap the addition for subtraction and things work basically the same, but I cannot swap the multiplication for division. That doesn't work. Okay, let's use the distributive property to simplify some things. So I have 9 times 5/9 y minus 1/3. As it is, I might look at this parentheses and say, can I simplify this? Not really, because I have two terms and they're unlike terms. One of them has a y to the first power, the other one does not have any y's, so can't simplify it. But maybe I can distribute. So I have A times B minus C. Well, that should make AB 9 times 5/9 y minus AC minus 9 times 1/3. Now I notice, well, 9 times 5/9 y, I can use the associative property of multiplication. This is 9 times 5/9 times y minus 9 times 1/3. And I know that 9 times 5/9 or 9/1 times 5/9. The 9s will divide out, leaving me with 5y. And of course, 9 times 1/3 is 9 divided by 3, or just 3. So this actually did end up simplifying pretty nicely, but using the distributive property. We didn't simplify the parentheses first. We distributed into the parentheses, and that let us simplify a lot better. Any questions so far? Okay, so what about this one? 5 times 2n minus 9 plus 12 times n minus 3. So again, I have inside of each parentheses, I have something that's already in simplest form, 2n minus 9. There are two terms there, and they're unlike terms. The 2n term has an n to the first power. The 9 term has no variables. They are unlike terms. We need to have the same variables to the same powers for them to be like terms and combine together. And same for the n minus 3, unlike terms. However, maybe I could simplify this if I use the distributive property. I'm going to use it once here and another time here. Okay, so the 5 times 2n minus 9 becomes 5 times 2n minus 5 times 9. I don't know what my deal is today. In my first class, I was also like, my handwriting was just terrible today. So plus, and then for my 12 times n minus 3 term, I have a 12n and 12 times n minus 12 times 3. These bits came from here. 5 times 2n is 5 times 2 times n, again, using that associative property of multiplication, or that's 10n, minus 9 times 5 is 45, plus 12n, 12 times 3 is 36, so minus 36. I would like to switch these two. I've got to be a little careful, though, because I can't just make this 10n minus 12n plus 45, because this minus is kind of attached to the 45, right? So maybe I'll rewrite this as 10n plus negative 45 plus 12n plus negative 36. I can always write subtracting a number as adding the opposite of that number, adding the negative of that number. I'm choosing to do that here so that all of my binary operations, a binary operation is something that takes two things as input and yields one thing as output. So like 3 plus 5 equals 8. It takes as input 3 and 5, the things on either side of the plus sign, and yields an output of one number 8. So all of my pluses have to the left and to the right positive numbers that are, or sorry, numbers, integers that are being added together. So now I can swap these two. I can use my commutative property of addition to make this 10n plus 12n plus negative 45 plus negative 36. And now I can use associative property. I can choose to add these two together to get 22n plus, and I can choose to add the second two together. Well, 40 plus 30 is 70. 6 plus 5 is 11. I think that's 81. And I'm adding a negative to a negative, so the answer is negative. Or this ends up being 22n minus 81. So I distributed. I was careful to multiply everything out, to use my properties carefully, not make mistakes with negative signs. It's really easy when you're using a bunch of properties in a row like this to miss a negative sign or something like that, or to be a little too flippant with your properties and do something like just swap the 12n and the 45 and accidentally get a minus 12n and a plus 45 when the signs should be the other way around. But I was just careful with all of it. It took a little bit of time to work through, but I don't think any individual step was really that difficult, but it's just being careful about these little details. Any questions so far? Now, a problem like this can be really tricky. 5m minus 3 minus m plus 7. We might be tempted to just do something like 5m minus 3. That parentheses doesn't really seem to be doing anything. And then like minus m plus 7 and go from here. I have a little bit of an issue with this, though. What would be the issue is, well, if I do just something like, say, a minus b, I think of that as being like a plus negative b, or really kind of like a plus negative 1 times b. I could write it that way also. Or in other words, this should be 5m minus 3 plus negative 1 times m plus 7. Now, this first parentheses truly isn't doing anything, so we can get rid of it. But I do notice that I have a factor of negative 1 that needs to distribute to both terms here. So I have negative 1 times m plus negative 1 times 7. So I see I do have 5m minus 3 minus m, but if I was a little too flippant about using my properties or getting rid of parentheses, I would have missed the negative sign on the 7. So this isn't quite correct. We need to take care and handle that minus sign properly. It needs to distribute through that whole m plus 7, which means negating the m and also negating the 7. Now let me choose to kind of rewind one step to here. And I'll think of this as 5m plus negative 3 plus negative m plus negative 7. Now everything is connected with pluses. I would like to get my like terms next to one another. I can use my commutative property of addition to switch the order of the minus m and the minus 3. 5m plus negative m, which is just 5m minus m, plus negative 3, which is just minus 3, plus negative 7, which is minus 7. Or now I see I have 5m's minus 1m is 4m, minus 3 minus 7 is minus 10. Any questions on distributive property so far? So we have problems where it's kind of clear we need to use distributive property. We have other problems like this with an application problem where it's not so clear how distributive property could apply. We don't need to use distributive property here, but it can be helpful. How much do 12 bottles of iced tea cost at a price of $1.95 per bottle? Well, the cost is going to be 12 times 1.95 in terms of dollars. And I could do this multiplication. Okay, that's fine. But I might notice that $1.95 is pretty close to $2. And in fact, if I were to ask you just just a real quick answer about how much is this going to cost, you're going to say $2 a bottle times 12, that's about $24. But if I wanted a precise answer, I noticed that it's easy to take $2 times 12. But 195 is just 2 minus 0.05, $2 minus 5 cents. And I can distribute, this is going to be 12 times 2 minus 12 times 0.05. 12 times 2 is 24. And 12 lots of 5 cents. 5 cents is like half of 10 cents. So what is that? I'm going to get 12 lots of 5 cents or 6 lots of 10 cents. So 24 minus 0.6 is going to be $23.40. This is probably easier and quicker, probably a lot easier and quicker than writing out 1.95 times 12, going through all of this, counting your decimal places, and so on, right? Recognizing that $1.95 is really close to $2 and it's easy to multiply by 2. So I could just rewrite $1.95 as $2 minus 5 cents. It's also not too bad to multiply by 5 cents. And that gives me my answer pretty quickly. Now, if I was looking for the cost of 12 bottles of tea that are a price of $1.63 per bottle, I'd probably choose to just go the brute force method, because $1.63, I mean, I guess I could write that as $2 minus 37 cents, if I said that right. I think I said 163. But like multiplying 12 by 37 cents is going to be just about as annoying as multiplying this. So, right, I'm leveraging the fact that I can split $1.95 into the sum or difference of two numbers, each of which are easy to multiply by 12. That was the case here. There's some examples where that's not the case, and then you just do it the kind of old method. Or in this example, find the total price of a $110 item with 8% sales tax. Well, the sales tax is the sales tax rate times the purchase price, and the total is the purchase price plus the sales tax. Or in other words, my total is the purchase price plus, but the sales tax is sales tax rate times purchase price. Well, purchase price I could just write as 1 times purchase price. And I see that this is just what I would get by distributing purchase price into 1 plus sales tax rate. So I could actually combine my two equations here into the total cost is the purchase price times 1 plus the sales tax rate. So instead of doing two separate problems, a multiplication, then an addition, I can basically, I still have to do an addition, then a multiplication, but this addition is really easy. So my total cost in this example is going to be my purchase price of 110 multiplied by 1 plus 8% or 1.08. 1 plus 0.08, 1.08. And then we're multiplying these two together. 8 times 0 is 0. 8 times 1 is 8. 8 times 1 is 8. We have a 0 here. And then 1 times 0, 1 times 1, 1 times 1. 2 decimal places, 0 decimal places. I should have 2 in the answer. So my total cost is $118.80. So we kind of use the reverse of the distributive property, right? We could choose to write A times B plus A times C as A times B plus C. That's what we did down here to get our answer in 1 step instead of 2 steps. I suppose we still technically did need to add and multiply. We still needed to do 2 steps, but this addition, just adding 1 plus a decimal, is super easy to do. Okay. Any questions? So we have some additional properties. We have the identity properties of addition and multiplication. It's quite important that these have identities and inverses. The whole way that this real number system is set up kind of requires the existence of identities and inverses. So the identity properties of addition and multiplication: a plus 0 equals a, or 0 plus a equals a. So we say that 0 is the additive identity. It's the thing that if we add it onto a number, we get the same number back. We don't change the value. Whereas a times 1 equals a. So 1 is the multiplicative identity. 1 is the number that if we multiply onto something, it doesn't change its value. So we have an additive identity 0 and a multiplicative identity 1 for our 2 operations, addition and multiplication. So we have identities for each operation. We also have inverses for each operation. We have that a plus negative a equals 0. So if I take a number and I want to add something to it to get the additive identity as a result, that number is the opposite. So the additive inverse of a is negative a. We call it the additive inverse because if I have a number, the additive inverse negative a is the thing I need to add to that number to kind of like cancel it out, to give me the additive identity back. The multiplicative inverse is 1 over a because a times 1 over a, that gives me a over a. That's just 1, the multiplicative identity. So the multiplicative inverse of a is 1 over a. And importantly, this is provided a is not equal to 0. More generally, the multiplicative inverse of the additive identity doesn't exist. It's undefined. So that's a more general kind of idea. Note that the additive inverse of the multiplicative identity 1, we can take the additive inverse of 1 and get negative 1. That's not a problem. but the multiplicative inverse of the additive identity, 1 over 0, that's undefined. And we have the zero property of multiplication. So we see that the multiplicative inverse of 0, basically the thing that I would need to multiply 0 by to get 1, doesn't exist. And that kind of makes sense because 0 times anything is going to be 0. How am I going to multiply 0 against something and get 1 out? The zero property of multiplication says exactly what I just said, that any number times 0 equals 0. Or therefore 0 over any number that's not 0 is 0. So note that a times 0 equals 0. If I have a number times 0, that gives me 0 back. If I divide both sides by a, that tells me that 0 equals 0 divided by a, where a is not 0. Because I don't want to divide by 0 over here. On the other hand, note that a divided by 0 is undefined. Why is that? Because if a divided by 0 was n, say some number that was a real number, well, this has an equivalent equation that a equals n times 0. But n times 0, by the zero property, is always 0. So this only is possible to make sense if a equals 0. So a over 0 is undefined if a is not 0. And we're not going to get into this nuance, but the idea is 0 over 0 really should properly be called indeterminate. We're not going to split these hairs. These are important hairs to split for later courses. But at this point, we're not going to really worry about undefined versus indeterminate. We're just going to say that kind of a over 0 is undefined. But we do see that if a equals 0, then saying 0 equals n times 0 actually kind of is a sensible thing to say. But the problem is that if I say 0 equals n times 0, what is n? Well, then n can be anything. So like 0 over 0, it's not that it doesn't make sense, it's just that it kind of can be anything. And it's very context dependent what it actually is. So that's the hair that we're not going to really split here. But we just don't want to divide by 0 because if nothing else, it's always going to cause a problem. Either resulting in something undefined or something that maybe an answer could exist, but we just don't know what it is. Okay, so for each of the following, let's try to find the additive and multiplicative inverses. So remember, the additive inverse of a number is negative of that number, and the multiplicative inverse is 1 over that number. So the additive inverse is going to be negative 12. It's the thing that I would add to 12 to get the additive identity. So since 12 plus negative 12 gives me the additive identity 0. And the multiplicative inverse is going to be 1/12, since it's the thing I need to multiply against 12 to get the multiplicative identity 1, since 12 times 1/12 equals the multiplicative identity 1. So when I'm multiplying, I'm looking to get multiplicative identity as a result. And when I'm adding, I'm looking to get additive identity 0 as the result. So if I'm looking at 3/8, what's the additive identity? It's going to be negative 3/8, since 3/8 plus a negative 3/8 When I add those two together, I get, as a result, the additive identity 0. Or for the multiplicative identity, I want to get 3/8 times the multiplicative identity equals the multiplicative inverse 1. So what is 1 divided by 3/8? Or maybe I could write this a little better as 1 divided by 3/8 like that. I want to invert and multiply. This is going to be 1 times 8/3, or just 8/3. So if I have a fraction, to get the multiplicative identity, I flip the fraction. 3/8 flips to 8/3. And I see that if I multiply these, the 8s are going to divide out, the 3s are going to divide out, and leaving me with just 1. 3/8 times 8/3, I multiply those, I get the multiplicative identity 1 as a result. So 8/3 is the multiplicative inverse of 3/8. Any questions so far? I know this is a bit more abstract than what we're kind of used to, but we're kind of taking this tangent to hopefully have a little better appreciation of how all of this fits together. We've kind of talked about a property here, a property there, but we're looking at them all in context now and seeing how they all interrelate. The zeros, the inverses, the identities kind of all interrelate with one another. Okay. And then if I look at, say, negative 0.2, what is its additive identity? So I want to say its additive identity is something, since negative 0.2 plus whatever I put here, when I add them together, I get the additive identity 0 out. What's the opposite of a negative number? It's just the positive of that number, 0.2. So the additive inverse of negative 0.2 is positive 0.2, since negative 0.2 plus 0.2 gives me 0. And my multiplicative inverse, again, I want to take negative 0.2, multiply it by something, and get the multiplicative identity 1. So my multiplicative inverse is going to be 1 over negative 0.2. That's not the nicest way to write this. Let's write it a little nicer. That's negative 1 over 0.2. I can bump my decimal in the denominator 1 to the right. If I do the same in the numerator, and I see I get negative 5 out. 0.2, that's like 20%, right? That's 1/5. Negative times negative gives me positive. 1/5 times 5 gives me 1. That looks right. I multiply negative 0.2 by negative 5. That multiplication does result in the multiplicative identity. So therefore, negative 5 is the multiplicative inverse of negative 0.2. Any questions so far? So a little question here. Is the following correct? If I wanted to make the statement, let me actually bump this down to the next line since it's a little small on the screen. There we go. It's on its own line. The equation editor makes the whole thing a little bit bigger. So is this sequence of statements here correct? 1/10 divided by 1 over 0. Well, I'm dividing by a fraction, so I invert and multiply. This gives me 1/10 times 0 over 1. But I'm multiplying two fractions. I multiply across the top. 1 times 0 is 0. Multiply across the bottom. 10 times 1 is 10. 0 divided by 10, well, going up here, the zero property of multiplication would say that this is 0. It seems like every step that I did is okay. I have a little bit of a problem though. So all of these addition rules and properties and algorithms and so on that we've discussed assume the numbers we're working with are real numbers. So when I say A divided by B over C divided by D, when I say I can invert and multiply, that assumes that this is a real number divided by a real number, or in this case, I suppose a rational number divided by a rational number. 1/10 is a real number, that's fine. But 1 over 0 is not a real number. So even though kind of after, in some sense, after I invert and multiply and simplify, I get 0, it's not a sensible thing to do in the first place. I can't do this. Now, if I started here and went forward, that would be fine. But I can't invert and multiply because, well, 1 over 0 is not a real number. It doesn't follow the same arithmetic that we've been working with, right? I can't count on the fact that 1 over 0 acts like a fraction, like 3/5 would act like, and invert and multiply and have that be okay. So no, the following is not correct. I can't take 1/10 divided by 1 over 0 and kind of make things work out okay. So I suppose the short answer is no, because 1 over 0, the thing I'm dividing by, is not a real number. Any questions so far? Okay, and then one last example in this discussion. So Carrie had to have 5 fillings done at the dentist. Each filling cost $80. Her dental insurance required her to pay 20% of the cost. Calculate Carrie's cost. So her cost is 5 fillings at $80 each, and she needs to pay 20% of that cost. So 5 times 80 times 20%. Now I could go ahead and just multiply 5 times 80, get that answer, multiply that by 20% or 0.2 and get that answer. That would be fine to do. But in problems like this, I always want to look for a bit of simplification. And there's a couple ways you could go about simplifying this. But I might notice that 20%, like if I have 20 cents, what fraction of a dollar is that? It's 1/5 of a dollar. 20% is 1/5. I could use my commutative property of multiplication to swap the 80 and the 1/5 and do 5 times 1/5 times 80. But wait, 5 times 1/5, that's a number multiplied by its multiplicative inverse. That yields the multiplicative identity of 1 times 80, or just 80. Because each filling I have to pay for 1/5 of the amount. That's the way the insurance works in this case. But I have 5 fillings. I need to pay for one of the fillings. I can either think of this as paying, like if I have, pretend these are teeth that need filled. I can either think that I pay for 1/5 of this one, 1/5 of that one. I can either imagine paying for 1/5 of each tooth, or I could imagine paying for one full tooth out of the 5. So those are two different ways to think about the same problem. This comes up in maybe more complicated ways in things like, for instance, pooling of risk for insurance companies. So the way insurance works is, you think of your car insurance, right? You pay some money into the pool, you pay the insurance company money. So there's this like big bag of money in here, and you pay in your $100 premium or whatever, and everybody else pays in a little bit. And this makes a bunch of money in this big bank account or this big pool of money that can be drawn from. And then occasionally, one person gets in a crash and, they make a claim on the insurance and they withdraw $2,500 from that pool. So if you get into a crash and you call your insurance agent, say, hey, I got in a crash, and they say, okay, here's how much we'll pay you to kind of cover that cost, or how much we'll pay the person that you ran into, or whatever it may be, the total cost of that accident is going to come out of the pool. Now, hopefully we have lots of people paying in a small amount and a few people taking out what, is typically a relatively large amount. If you were paying the whole amount of a car crash every month for a premium, you just wouldn't have insurance. Or, well, I guess you have to have insurance, but you know what I mean. You would rather not have insurance in that case. So you're going to typically be paying in to the pool much less than, say, the average crash. So you have lots of people paying in a little bit, and then a few people taking out a bunch, the few people who get into a crash. So how much should I charge each person? I mean, what I'd really like to do is, if I knew that this person, Bill Smith, was going to be a really high risk and get in a bunch of crashes, I would like to charge Bill Smith a bunch of money, kind of what his average cost per year is going to be for his own crashes. And if, Susie over here was a really safe driver and hardly ever got in any crashes, I would like to charge her a very low amount, because on average over 10 or 20 years, I'm not going to have to pay very much out for her any crashes that she's involved in. But at the outset, I don't know that. I know that there, in this pool of 100 drivers, there are some Bill Smiths who are going to cost me a lot, and some Sallys who are going to cost me a little, and some people who are in the middle who are going to cost me, a moderate amount. But I'm not sure who's who. Right? Ideally, I would like to find, the sore tooth, the Bill Smith, and just charge him a lot and charge other people not very much. But in reality, I kind of just say to each person, well, okay, I mean, especially if I don't have a lot of experience with you, if you haven't been with my company for a long time, um, I'm going to basically charge you the average amount. You know, I'm going to treat you like, if 10% of my drivers are bad drivers who cost me a lot of money, like, I'm going to pretend that you're like 10% of a bad driver. And if 50% of my drivers are moderate drivers that cost me a moderate amount of money, I'm going to pretend that you're like 40% of a moderate driver. And then, or whatever the numbers were, I forget where I left off with my numbers, but you can treat each insured as if they are individually kind of like part good driver, part moderate driver, part bad driver, and come up with their premium that way, because you don't know like who the bad driver is in the pool. uh you kind of treat everybody like they're, part good driver, part moderate, and part bad driver. You kind of treat them like this, when in reality it's more like this. But you could slice and dice it either way and get the same result, where you have enough money in the pool to pay out the claims that need to be paid out. Now, ideally, over time, maybe 5 years later, if you have experience, 5 years of experience with all these 100 folks, you'll have seen, oh, well, these people haven't filed a claim in 5 years. That's a little more evidence that they're good drivers, and a little more evidence that they're not bad drivers. So their premium might be adjusted in light of that. And the person that got into 3 accidents in 5 years, maybe their premium goes up, because with more experience, I can narrow down who the good, moderate, bad drivers might be. Um, But again, it's just kind of two different ways of thinking about it. And we can see that coming through in the algebra and the arithmetic. We also can see that just like pictorially like this. Okay. As kind of an aside, when people say, oh, insurance is so expensive, well, for things like health insurance, for things like car insurance, your goal is to not use it, right? Or for homeowners insurance, like you don't like you're not happy when you get to use your homeowners insurance or your car insurance. That means you got in a crash. It's a big hassle. You have to get your car fixed. You have to make claims, and right at the very least, it's going to cost you like 10 hours of time. And it's probably going to cost you some money too. Um, where health insurance, like ideally you use your health insurance. You like go to the doctor and the insurance pays some to the doctor and so on. So health insurance isn't really as much like car or homeowners or life insurance. It's not like you pay in a little amount because there are a few people, sometimes it's you, sometimes it's somebody else who has to take out a large amount. It's kind of like everybody pays in a moderate amount and like mostly everybody takes out a moderate amount. So, you know, you're still basically paying your doctor. Like if you go to visit your doctor, you're still basically, just paying what you'd pay at the front desk. There are a couple of nuances to that. Number one, the insurance company can usually negotiate a better rate. So if you were literally just paying at the front desk with cash, um, you're probably not going to get as good of a rate as the insurance company gets because they have more bargaining power. So that's one thing. Um, but the point is there's kind of a floor to how low health insurance can get. You can't, you can say if people drove safer and got in fewer crashes, we would need to pull less out of the pool and we need to charge people less money. But it's not really like, with health insurance, it's not like if you did things better, then health insurance would cost less. I mean, you're still going to want to go to your doctor and get checked and get blood work and that kind of stuff. But health insurance does have a side where it is a little bit like this, right? If somebody gets cancer and wants a, immunologic treatment that costs $100,000 or something, they're going to be taking a lot out of the pool. And if you want to not have insurance until you need it, well, that's kind of like saying that, all of these $100 people, like nobody's paying in premiums until they get in a crash, and then they're happy to pay the $100 premium to get the $2,500 out. The math just doesn't work then, right? You're paying the $100 to insure yourself against downside risk, expecting that most of the time you're not going to have to use it. But if I say I only want to pay the $100 in the months where I end up having to use it and making a claim, well, then you have a few $100 coming in and a few $2,500 coming out. You can't make that balance, right? We need a lot of $100 coming in to balance with the few $2,500 going out. So a little bit of insight and thought into maybe how insurance works and how that relates to some of these ideas, right? That instead of just being 5 fillings, each paying 20% of the cost, this would be like, one crash with 25 individuals paying a premium in, and each of them are paying for like 1/25th of that crash with the premium that they put into the pool. That, that one individual is getting 25 other individuals' premiums, or I suppose their own premium plus 24 other individuals' premiums. So this kind of an idea with this multiplicative identity and inverse kind of idea can apply more generally as well. Right. Are there any questions on any of this? So the next topic goes into measurement systems. So I think we're going to break here. I think getting through 7.1 through 7.4, getting through 4 sections in a day is already a pretty big ask. And I know it was a lot of material. Hopefully it was a good bit of review of some of these properties, but maybe just in a slightly different context with the idea of this real number system in mind, and kind of seeing all of the properties back to back, how they all connect and interrelate. Any questions on any of this before we break for today?